You know, when you think about primary school math, you often picture, well, the real basics, don't you? Adding little numbers, times tables, maybe some simple shapes.
Building blocks?
Exactly, that's where it all starts. But then it seems like something really changes around year 5. Kids are about 9 or 10 then.
That's right, typically.
And the material we've been digging into today, it actually calls it a critical juncture. It sounds less like just, adding more facts and more like they're starting to think about maths in a completely different way, building new things.
That's a really good way of putting it, yeah. This deep dive is focused squarely on year.
And this source, it's not just a leaflet, is it? It looks like a pretty hefty report. Feels like it's aimed at people really involved in primary maths teachers, maybe curriculum leaders.
Definitely. Or even, as you say, very keen parents who want to understand what's going on. It looks closely at the Year 5 program of study. That's the official what they need to learn. But crucially, it puts just as much weight on the pedagogical approaches.
The how they teach it.
Exactly, the how. And the report is super clear on this. The what and the how are, and I'm quoting here, inextricably linked. You can't separate them.
That makes sense. You can't just throw complicated ideas at kids without thinking about the best way to actually teach them.
Absolutely. You won't really get a handle on the demands of Year 5 maths or, the hurdles it presents for kids unless you understand the teaching principles that are seen as vital for success at this stage.
Okay. So our mission today then is to unpack this report, pull out the really key stuff.
That's the plan. What makes Year 5 so different? What are these essential teaching methods everyone's talking about? And importantly, how does getting Year 5 right actually set kids up for what comes next in maths?
Right. So whether you, listening, are maybe dealing with Year 5 homework right now, or perhaps you teach this age group, or maybe you're just curious about how we build mathematical thinking, from playing with blocks to abstract equations, this should give you a good overview. A shortcut, maybe?
Hopefully. We want to explore the core bits, maybe some surprising details about what and how they learn, and really understand why Year 5 is such a linchpin year.
Okay, I'm ready to dive in. I've got my questions ready.
Great. It's a fascinating stage to explore, genuinely.
All right, let's kick off with the how then, the pedagogy. You said the report spends a lot of time on this, explaining why how you teach in Year 5 is so important.
Yes, it really does. Right from the start, the emphasis on pedagogy is strong. The report basically argues that you can't teach the Year 5 content, effectively the fractions, the long multiplication, all that stuff, without using the right methods, just sort of surface level learning. It's not going to work when things get this complex.
Right, rote learning isn't enough anymore.
Exactly. The way concepts are introduced, how kids explore them, how they're connected, that's what matters most.
It makes sense. As the ideas get trickier, the support, the teaching has to be cleverer too. And the main approach being pushed here, the sort of engine for Year 5 maths, is this thing called teaching for mastery.
That's the one. Mastery is, well, it's become the dominant philosophy in English primary maths. Organizations like the NCETM, the National Center for Excellence in the Teaching of Mathematics, they really champion it. And at its core, there's this really powerful belief: all pupils can achieve a high standard in maths.
All pupils. That feels like a big shift from older ideas where some kids were seen as maths brains and others weren't.
It's a massive philosophical shift, yeah. It moves away from that idea of labeling kids early on or expecting this huge spread of attainment where some fly ahead and others get left behind. The mastery approach means the whole class generally progresses through the curriculum content at broadly the same pace, as the report puts it.
Okay, broadly the same pace. But hang on, kids learn differently, right? Some pick things up faster, some need more time, some grasp it deeper. How does same pace actually work in a real classroom?
That's a key question, and mastery deals with this through differentiation. But, and this is important, the report makes it clear, it's not about giving different groups of kids completely different maths, tasks, or topics.
Ah, okay, so not like you do the easy sums, you do the hard problem.
Not really, no. Differentiation in mastery is more about varying the depth of thinking and the complexity of the problems within the same topic. So everyone might be learning, say, adding fractions with related denominators. But some pupils might need more support, perhaps different physical resources, while others who've grasped the core idea quickly might be challenged with more complex examples, non-standard representations, or multi-step problems that really push them to apply that fraction knowledge in new ways.
Okay, so it's like everyone's working on fractions, but some are exploring the concept more deeply or tackling trickier applications of it.
Exactly. Keeping the whole class learning together on the core concept, but stretching and supporting appropriately. And the report argues this isn't just a nice idea, it's a functional necessity for Year 5.
A necessity. Why?
Because Year 5 demands more than just knowing facts. It requires genuine fluency being efficient and flexible. It needs strong reasoning skills explaining the why. And it demands sophisticated problem solving. The curriculum explicitly says kids should be able to decide which operations and methods to use and why. That kind of strategic thinking, that only comes from deep, connected understanding. Rote learning won't get you there.
So mastery is designed to build that specific kind of deep, flexible understanding that Year 5 requires. Okay, and the report unpacks this mastery approach through, what do they call? The 5 big ideas.
That's right. The NCETM's 5 big ideas. They're seen as the essential ingredients, if you like, for every effective mastery lesson. The first one is coherence.
Coherence in a math lesson.
Yeah, it means everything is really carefully planned and sequenced. Lessons aren't just random activities. Learning is broken down into small logical steps, and each new step clearly builds on what kids already know. It's about making maths feel like a connected journey, not just a collection of isolated facts or tricks.
Like building a wall brick by brick, making sure each one rests securely on the one below. Very deliberate.
That's a great analogy. Very deliberate. The second big idea is representation and structure. This is all about the careful choice of tools, physical things like blocks or counters, but also diagrams, pictures, visual models. The key here is that they're not just used to get the answer. They're chosen specifically to expose the underlying mathematical structure.
To help kids see the maths, make the abstract ideas visible.
Precisely. Like using place value counters, not just to show a number, but to physically demonstrate what happens when you multiply by 10, how the digits shift. It makes the concept tangible.
Got it. What's next?
Third is mathematical thinking. This is huge. It's about actively getting pupils to think like mathematicians. So encouraging them to spot patterns, to make links between different bits of maths, to make predictions or conjectures, and really importantly, to explain their reasoning using proper mathematical language. It's about the thinking process, not just the final answer.
So getting them to articulate the how and the why?
Exactly. Fourth is fluency. And we touched on this, but in mastery, it's much more than just being quick with times tables, although that's part of it. Real fluency combines being efficient with calculations and having the flexibility to move between different mathematical contexts and representations. It means understanding the relationships between numbers, grasping concepts deeply, and crucially being able to choose the best method for a particular problem.
Ah, so knowing when to do it in your head versus when you need to write it all down, that strategic element again.
Yes, that strategic decision-making is key to fluency. And the fifth big idea is variation. This is a really powerful teaching technique.
Variation. How does that work?
It's about the teacher purposefully changing the questions, examples, or the way something is represented in a carefully planned sequence. The goal is to draw the pupil's attention to a key feature of the concept or the procedure they're learning.
Can you give an example? That sounds a bit abstract itself.
Sure. The report talks about 2 types. Conceptual variation might be showing the fraction, say 2/3, not just as 2 shaded parts of a circle divided into 3, but also in a point on a number line between 0 and 1, or as 2/3 of 12 apples. It helps them see that 2/3 is one mathematical idea with multiple faces, if you like.
Okay, showing the same idea in different ways to deepen understanding.
Exactly. Then there's procedural variation. This is more about structuring practice questions. Imagine learning subtraction with borrowing or exchanging. The teacher might give a sequence of problems. First one with no borrowing, then one needing borrowing from the tens, then one needing borrowing from the hundreds, then maybe borrowing across 0. Each small change highlights a specific step or challenge in the procedure.
Ah, so the sequence of questions itself teaches something, guiding them to notice the key difficulty or pattern.
Precisely. It stops pupils just mindlessly following steps without thinking, makes the learning much more focused. And the report says the primary vehicle for actually doing all this mastery stuff in the classroom, for bringing these 5 big ideas to life, is the concrete pictorial abstract model, or CPA.
CPA. Right, I've heard of that. Concrete Pictorial Abstract.
Yeah.
Fundamental stuff in primary math.
Absolutely fundamental. It comes from Jerome Bruner's work. It gives teachers a structure to help children bridge the gap between hands-on, physical experiences and the abstract world of mathematical symbols. Should we quickly recap the stages?
Yeah, let's do that. Concrete first, that's the doing stage, right? Using actual objects.
Exactly. Pupils manipulate physical things, counters, cubes, Denny's blocks for place value, maybe fraction tiles, Cuisinart rods. The report makes a really important point here.
Mhm.
This isn't just for younger kids or those who are struggling. No, it's for all pupils, especially when they meet a new concept for the first time, or when they need to deepen their understanding of something tricky, even in year 5. That physical interaction is often essential to grasp the basics of a new idea.
So, a year 5 people learning, say, how to multiply a fraction by a whole number might actually start by physically grouping fraction tiles.
They very well might, yes.
Yeah.
It makes the abstract calculation make sense. Then comes pictorial, the seeing stage.
So, drawing it.
Essentially, yes. Using visual representations. This could be drawing simple pictures, using diagrams, perhaps arrays for multiplication, or very importantly in year 5, using things like the bar model to represent problems.
Okay, so moving from handling objects to representing them visually.
Yeah, and this stage is described as a crucial bridge to the abstract symbols. It helps kids visualize the mathematical structure.
And finally, abstract. That's the numbers and symbols we usually think of as maths.
Correct. This is where pupils use the conventional notation numerals, the plus minus times, divide signs, equal sign, fraction notation, decimal points, percentages. They're working purely with symbols.
But it's not just a simple journey. Concrete, then pictorial, then abstract. Finished, the report stresses it's more dynamic.
Absolutely vital point. It's not linear. Good CPA teaching involves moving fluidly between these stages. A teacher might introduce something concretely, model it pictorially, let pupils practice abstractly, but then if a pupil gets stuck or needs to explain their thinking, they might go back to drawing a picture or even using the concrete materials again.
So you might solve a sum abstractly and teacher says, okay, show me that with the blocks.
Exactly. Or, can you draw a picture to prove your answer? Using all 3 modes together and moving between them builds really strong, flexible, interconnected understanding. It gives kids multiple ways to see and grasp the maths.
That makes so much sense. It's not just about finding the answer, but understanding it from different angles. And this whole pedagogical package mastery, the big ideas, CPA, it sounds like it's all geared towards building that deeper thinking needed for the tougher stuff in year 5. The report mentioned a significant escalation in reasoning and problem solving.
It really did. Year 5 is definitely where word problems, for example, get more complex. They often involve multiple steps and might require pulling in knowledge from different areas of maths, maybe using fractions and measurement in the same problem.
And reasoning in year 5 means more than just showing you're working.
Oh, much more. It's about justifying why you chose a particular method, following a logical path to a solution, explaining your steps clearly using accurate maths language, and basically building a convincing argument for your answer. It's the why and how, not just the what. The report also notes that problems are often set in real-world contexts, money, time, measurements, to make sure kids can actually use their math skills flexibly.
And do they learn specific techniques to tackle these more complex problems? You mentioned the bar model earlier.
Yes, they are explicitly taught problem-solving strategies, sometimes called heuristics. And the bar model gets a special mention in the report as an invaluable tool for year 5.
How does it help?
Well, it's a pictorial strategy. It helps pupils visualize the information in a word problem. They draw bars to represent the different quantities or parts of a whole described in the problem. This visual structure helps them see the relationships between the numbers, figure out what they know and what they need to find, and then plan the calculation steps needed.
Ah, so it turns confusing sentences into a clearer visual map of the problem.
That's a perfect way to describe it, a visual map. It really bridges the gap between the words and the required calculations.
So, yeah, we've established the how this mastery-driven CPA-supported pedagogy is crucial. Shall we now get stuck into the what? What specific maths topics do year 5 pupils actually learn? Right. Let's dive into the curriculum domains. The report breaks it down, showing how mastery and CPA apply to each area. We don't need to list every single objective, but maybe the key developments in each.
Sounds good. Let's start with number and place value. What's the big story here?
Big numbers. They properly get into numbers up to 1 million. Reading them, writing them, comparing and ordering them, understanding the value of each digit, knowing the 7 in 750,000 is 700,000. They also count forwards and backwards in steps of powers of 10, like 10, 100, 1,000, from any number up to 1 million.
Wow, up to 1 million. That feels like a significant jump in scale. And negative numbers come in properly, too.
Yes, often introduced using practical contexts like temperature scales or maybe sea level. They need to be able to count forwards and backwards through zero. Rounding gets extended too, rounding these big numbers to the nearest 10, 100, 1,000, all the way up to 100,000. Oh, and Roman numerals continue, up to 1,000, which is M. They practice reading years written that way.
Okay, massive numbers, negative numbers, big scale rounding, Roman numerals. How on earth do you teach kids to understand a million, rather than it just being a word with lots of zeros? Back to CPA. Absolutely essential here. The report flags place value counters and continuous charts as invaluable. Place value counters are brilliant because they let kids physically represent large numbers and, crucially, see what happens when you multiply or divide by 10, 100, 1,000. The
Right.
counters literally move columns on a place value grid.
So the abstract rule about moving the decimal point or adding zeros becomes a physical action they can see and do.
Exactly. It grounds the concept. Yatenyo charts offer a really powerful visual structure for understanding powers of 10, too. And mastery, especially variation, is used to build deep understanding. The report stresses getting kids to see numbers flexibly, understanding that 47,500 is, yes, for 10,000s, 7,000s, 500s, standard partitioning, but also thinking of it as 47,000s and 500s, or even 407,000s, non-standard partitioning.
Why is that non-standard way important?
It's crucial for mental calculation and estimation. If you can see 47,500 as 47,000s, it makes mental subtraction of, say, 2,000 much easier. It builds number sense. And number lines are used a lot, too, to help visualize the position and relative size of these large numbers and to support reasoning about rounding.
Okay, that makes sense. Moving on from the size of numbers to doing things with them, the four operations. What's new in year 5 for adding, subtracting, multiplying, and dividing?
It's a mix of consolidation and significant extension. For addition and subtraction, they're expected to be pretty fluent with the formal column methods, now extended to numbers with more than 4 digits. They also keep working on mental strategies for bigger numbers, and using rounding to check if an answer seems reasonable is really emphasized. Plus, as we said, multi-step problems where they have to choose the right operation.
Right, the calculations get bigger, and the thinking about which calculation gets harder. What about multiplication and division?
Big steps here. A major milestone, according to the report, is learning formal long multiplication. That's multiplying numbers up to 4 digits by a 2-digit number.
Ah, the one with multiple rows of working out? Tricky?
You can? Yeah. And for division, the focus is formal short division, dividing numbers up to 4 digits by a 1-digit number. But a really key skill here is learning to interpret remainders appropriately.
What does that mean, interpret remainders?
It means understanding that the remainder isn't just what's left over. Depending on the problem's context, you might need to round the answer up, like if you need whole buses for people. Ignore the remainder, if you're sharing sweets equally. State the remainder as the answer, how many are left. Or even express it as a fraction or a decimal.
Okay, so the math connects directly back to the real-world situation of the problem. That makes sense. What else falls under operations?
Number properties become more formal. Understanding factors, numbers that divide into another number exactly, and multiples, numbers in the times tables. Identifying prime numbers, those only divisible by 1, and themselves up to 100, and actually needing to recall the primes up to 19. And learning about square numbers, like 4 by 4 is 16, written 4 down all, and cube numbers, like 3 by 3 by 3, 27, written 3 to centaries, including the notation.
Factors, multiples, primes, squares, cubes, long multiplication, interpreting remainders. Wow, that's a packed domain. How does the pedagogy help them cope with all this?
Again, it's that balance, procedural fluency, getting the calculations right,
Yeah.
and conceptual understanding, knowing why they work. Formal methods are taught explicitly, but place value counters are brought out again to model the processes. For column methods, they physically show the exchanging or regrouping, carrying tens in addition, borrowing and subtraction. It makes those abstract steps concrete. For multiplication, arrays or counters can model the process. For division, they can physically share out counters or group them. Alongside this, they build their mental strategies toolbox. But the real goal of mastery here is fostering that interplay, helping kids make smart strategic decisions.
Choosing the best tool for the job.
Exactly. Looking at, say, 35,008 subtract 10,003 and realizing you can probably do that mentally versus 27,345 subtract 18,876, which definitely needs the formal written method.
Yeah.
It's about efficiency and understanding, not just blindly applying one algorithm.
Okay, got it. Now on to potentially the trickiest area for many people, fractions, decimals, and percentages. The report calls this a significant conceptual leap.
And it really is. This is where these three concepts, which are just different ways of representing parts of a whole, really start to intertwine. For fractions, they learn to compare and order fractions where the denominators are related, meaning one is a multiple of the other.
Like comparing quarters and eighths or thirds and sixths.
Exactly. They need to find common denominators, often visually first. They also learn to add and subtract fractions with the same denominator and now also with related denominators. They work with improper fractions, top-heavy ones like 53, and mixed numbers like 1 and 23, and crucially, learn how to convert between these two forms. And a new operation appears, multiplying proper fractions like 14 and mixed numbers by whole numbers.
So calculating things like what is 3 lots of 15 or what is 2 times 1 and 34.
Yes, exactly. And often starting with diagrams to make sense of it. Then decimals expand. They go down to thousands now. They learn to relate thousands to hundredths and tenths. They round decimals up to 3 places to the nearest whole number or to 1 decimal place. They read, write, order, and compare numbers with up to 3 decimal places.
3 decimal places. And percentages make their debut.
Yes. Year 5 is the formal introduction. They learn the percent symbol means out of 100. They start understanding percentage is just a special type of fraction with 100 on the bottom. They learn to write simple percentages like 50%, 25%, 10%, 75% is their equivalent, fractions and decimals. So knowing 50% is the same as 12, which is the same as 0.5.
Phew. Fractions, decimals, percentages, converting between them, doing calculations. How do they possibly teach this so it sticks and makes sense? It sounds incredibly confusing.
It can be, which is why the CPA approach is non-negotiable here. The report emphasizes using fraction walls or tiles, those concrete and visual bars for understanding equivalence, comparing, adding, and subtracting. They make the relationships visible. Bar models are also highlighted as really useful pictorial tools, especially for multiplying fractions by whole numbers or for finding fractions of an amount like 23 of 15 pounds.
So making these abstract fraction operations visible really helps.
Massively. And for linking fractions, decimals, and percentages, 100 squares are invaluable. You shade, say, 30 squares. The pupils can see it's 30 out of 3,100, which simplifies to 310. They can see it represents 0.30 or 0.3, and they know it's 30%. It makes that percent means out of 100 idea crystal clear.
That visual link across all 3 representations sounds powerful.
It is. And mastery's focus on coherence is critical. Teachers need to constantly stress that fractions, decimals, and percentages are just different languages for talking about the same amount. Using things like number lines, where you mark 14.25 and 25% all at the exact same spot, really reinforces this fundamental equivalence.
Right, anchoring them all together. Okay, let's move on to measurement. This feels a bit more hands-on, maybe.
It often is, yes. And its real power in year 5, according to the report, is providing a practical, meaningful context for applying and reinforcing all those number skills we've just talked about.
So what do they actually measure and calculate?
They learn to convert between common metric units, kilometers and meters, grams and kilograms, milliliters and liters. They also need to know some approximate imperial equivalents, like roughly how many centimeters are in an inch, kilograms in a pound, or liters in a pint. They calculate the perimeter of composite rectilinear shapes.
Composite rectilinear. Sounds complicated.
Just means shapes made up of rectangles stuck together, like L shapes or T shapes. Finding the perimeter often involves adding several lengths and sometimes figuring out missing side lengths first. They also calculate the area of simple rectangles and squares using standard square units like cm or mi1ors. They estimate volume, often by counting or building with 1 centimeter of blocks, and capacity, perhaps by measuring liquids. And work with time, including conversions, continues.
Okay, so lots of practical activity. How does that consolidate number skills?
Well, think about it. Converting meters to kilometers involves dividing by whole thousand. That's place value in decimals right there. Calculating the area of a rectangle might mean multiplying decimals if the sides aren't whole numbers. For example, 2.5 meters by 1.8 meter. Finding the perimeter of those composite shapes uses addition and often deduction. And solving measurement word problems frequently involves multiple steps, maybe converting units, then performing a calculation. The report calls measurement a powerful tool for consolidating and applying number concepts.
Ah, I see. So measurement tasks become real-world number problems. Makes sense. What about geometry? Shapes in space.
Geometry in year 5 gets more analytical. They learn to identify 3D shapes from 2D pictures like nets or drawings. They have to distinguish between regular polygons, all sides equal, all angles equal, and irregular polygons. There's a big focus on angles, estimating angle sizes, comparing them, measuring them accurately using a protractor, and drawing specific types acute, obtuse, reflex.
Using a protractor, that's a key practical skill.
Absolutely. They also learn important angle facts. Angles at a point add up to 360 degrees, angles on a straight line add up to 180 degrees, and recognizing angles that are multiples of 90 degrees. They use properties of shapes, like knowing rectangles have 4 right angles, to deduce missing lengths, or angles. And in position and direction, they learn to describe and perform reflections and translations, sliding shapes, understanding that the shape stays the same size and shape.
So it's moving beyond just naming shapes to understanding their properties and how they relate to each other. More reasoning involved.
Exactly. Practical exploration is still key handling 3D shapes, concrete using protractors accurately, concrete tool maybe using mirrors for reflection, concrete pictorial. But the emphasis is on reasoning, justifying why a shape is irregular, or deducing a missing angle in a rectangle because you know the properties of rectangles.
Understanding the rules of shapes, not just their names.
Okay.
And the last domain, statistics. What's the focus here?
It's mainly about interpreting data. Reading information from tables becomes more complex, including understanding real-world formats like timetables. They're also introduced to a new type of graph, the line graph.
Line graphs, usually showing changes over time.
That's typically how they're introduced, yes, showing things like temperature changes through a day, or maybe rainfall over a month, or someone's height growing over time. The key skill, though, across all data types, tables, graphs, is solving problems using the information presented, comparing values, finding sums, calculating differences.
So not just reading the data, but using it to answer questions.
Precisely. And again, the report suggests using authentic materials, real bus timetables, weather charts to make it relevant. Like measurement, statistics problems are often multi-step and require calculations. A timetable question might ask, how much longer does the 9.15 train take to get to London than the 10.30 train? You have to find the relevant times from the table first, then calculate the difference. It reinforces calculation skills, especially with time, in a meaningful context.
Right. Another area where number skills are applied to real-world info. Okay, so we've covered the how, the mastery pedagogy, and the what, the key curriculum areas. How does this all come together in a typical Year 5 lesson? And how does it prepare them for, well, the end of primary school tests?
Good questions. The report paints a picture of a structured, purposeful sequence for a mastery-aligned lesson.
What does that structure look like? Is it always the same?
There's a common flow. It might start with an anchor task, a problem or activity designed to get everyone thinking about the concept for the day, something accessible but thought-provoking. Then usually a quick recap to activate relevant prior knowledge. After that comes the main teacher input or guided practice, where the teacher explicitly teaches the new concept, modeling it carefully using CPA, moving between concrete, pictorial, and abstract as needed.
So the teacher is really demonstrating and explaining, using the resources.
Yes, very actively. This is followed by what's called intelligent practice. This isn't just random sums. It's a carefully designed sequence of questions, using that variation idea we talked about, to build understanding step by step and secure the new learning. Then comes independent practice, where pupils apply what they've learned.
And is this where that differentiation by depth happens?
Often, yes. Everyone's working on the same core concept from the lesson, but the tasks might vary. Some pupils might have extra scaffolds, like sentence starters for reasoning or specific manipulatives nearby. Others who are ready might tackle diving deeper challenges, problems that require more complex application or reasoning about the same concept. Finally, there's usually a plenary or reflection time at the end.
What happens there?
It's a chance to consolidate the learning, perhaps share different strategies pupils used, address any common mistakes or misconceptions, and make sure the key mathematical point of the lesson is clear.
It sounds very intentional. Every part has a purpose in building that deep understanding. You mentioned resources being key. What are the absolute must-haves for a Year 5 mastery classroom? The report mentioned a table too.
Yes, it references a table listing useful resources, but highlights a few as particularly crucial for Year 5, explaining why they fit the pedagogy. It stresses that a mastery classroom should be rich in physical and visual resources.
So what are the essentials?
Place value counters get another big mention. The report suggests their uniform size helps bridge to abstract value better than, say, Dean's blocks at this stage. They are seen as essential for modeling, multiplying, dividing by powers of 10, and for physically showing the exchanges in column calculations.
Making those algorithms transparent.
Exactly. Fraction walls or tiles are considered vital for that visual linear understanding of fraction equivalence, comparison, addition, and subtraction. It just makes it easier to see than abstract symbols alone.
Makes sense. You can literally see that 2/4 makes a half.
Precisely. Then 1 centimeter locks are needed for properly exploring volume and also for making square and cube numbers tangible, actually building a 3 by 3 square or a 2 by 2 by 2 cube.
Seeing squared and cubed as actual shapes.
Yes, protractors are obviously essential because measuring and drawing angles accurately is a specific curriculum goal, and the report says hands-on use is non-negotiable. You just can't learn it theoretically.
Got to practice with the tool itself.
Right. And 100 squares are flagged again as excellent visual tools for explicitly showing percent out of 100 and demonstrating those crucial links between fractions as hundredths, decimals, and percentages.
It really sounds like having these tools readily available is fundamental to making the CPA approach work across all the different maths topics. Okay, last big question perhaps. How does all this intense Year 5 work feed into the end of key Stage 2 SATs in Year 6?
The report tackles this head-on, and the message is very clear. Yes, Year 5 is crucial preparation for SATs, but effective preparation is not about doing practice test papers in Year 5.
Oh, so no early SATs drilling.
No. The report argues strongly that the best SATs preparation is simply building that deep, secure, and flexible knowledge, which the mastery approach aims for. It actually quotes, "The most effective form of test preparation is high-quality teaching."
So basically, teach Year 5 really well, focusing on understanding, and the SATs will take care of themselves.
That's the gist. The SATs papers, the arithmetic one and the reasoning ones, are designed to test exactly the kinds of skills and understanding that this Year 5 mastery curriculum focuses on building.
How does that mapping work?
Where the arithmetic paper directly tests procedural fluency, can they calculate accurately and efficiently with whole numbers, fractions, decimals? That's precisely what the Year 5 focus on mental and formal methods supported by CPA develops.
All that practice with column methods and fraction calculations.
Exactly. And the reasoning papers. They assess problem solving, often multi-step in context, justifying answers, applying knowledge flexibly. The report calls this kind of reasoning and problem solving the cornerstone of the Year 5 curriculum. So all that work on mathematical thinking, using bar models, explaining your methods that's directly preparing them for the reasoning papers.
The report even connects specific Year 5 objectives to sample SATs questions, doesn't it? Like showing how long multiplication from Year 5 appears in the arithmetic paper, or interpreting remainders or line graphs in the reasoning papers.
Yes, it draws very direct lines. The argument is compelling. Focus on high-quality teaching of the Year 5 curriculum, using mastery principles, building deep understanding, fluency, and reasoning, and you are, by definition, providing the best possible preparation for the assessments. It builds lasting knowledge, which is much more robust under pressure than knowledge gained through last-minute cramming.
It really paints Year 5 as the year where the foundations are not just built upon, but where the whole approach to mathematical thinking solidifies, setting them up for the future, not just a test.
That's a perfect summary. It's a truly pivotal year.
So, wrapping up this deep dive, it's really struck me how Year 5 maths isn't just more difficult sums, it's a significant shift. And this report makes a very strong case that you can't separate what they learn in that challenging curriculum from how it's taught.
That's absolutely the core takeaway. The teaching for mastery approach, using CPA dynamically, isn't just presented as a good idea. It's framed as the essential way to build the deep understanding needed at this stage.
It seems designed to build that coherent understanding, that genuine fluency, which includes smart thinking and those reasoning skills that are so demanding in Year 5.
And the goal isn't just ticking off curriculum objectives. By focusing on this kind of high-quality, pedagogy-first teaching, the aim is to build pupils' confidence and give them a really solid, lasting grasp of these fundamental mathematical ideas.
And the benefits go beyond Year 6 and SATs, right? The report implies it's about creating, what's the phrase? Resilient, flexible, and capable mathematical thinkers, ready for secondary school and beyond.
Exactly. Nurturing mathematicians, not just human calculators.
It's fascinating. This whole deep dive into the way Year 5 maths is taught really underscores its importance, especially as the ideas get more abstract. It certainly makes me think about my own experiences learning some of this stuff.
Well, that leads nicely into a final thought for you, the listener, to ponder. Thinking back on your own school days, especially when you encountered things like fractions, decimals, long multiplication, maybe percentages, how did it feel? Was your understanding built up through this kind of structured way, moving between seeing, doing, and symbols? Or does this mastery in CPA approach sound quite different from your experience? Does exploring Year 5 pedagogy like this give you any new insights into how we really build that deep mathematical foundation? What part of this Year 5 journey we've discussed resonates most, or perhaps least, with your own learning story?
Definitely food for thought. It gives me a much greater appreciation for the complexity and the vital importance of what goes on in those Year 5 classrooms. Thanks so much for guiding us through that.
My pleasure. It's a crucial year to understand.